Welcome to my talk. So first, thank the organizers for giving me the opportunity to speak here. I'm really happy to be here and to see so many Tensor Network people in person. So I'm going to talk about how we derived an effective field theory for holographic random matchgate tensor network. And I put holographic in brackets here because while the motivation of this project certainly started out in the realm of how tensor networks shed some light on ADS-CFT duality and holographic dualities in general, the main part of my talk will actually be not concerned so much with that, and I certainly don't want to claim to make any significant insight into the holography aspects. But nevertheless, I think we developed quite a nice theory that establishes the correspondence between matchgate tensor networks and free fermionic Hamiltonians, and in the case of random matchgate Hamiltonians, the correspondence to nonlinear sigma model. And also along the way, we encountered some nice mappings between matchgate tensor networks, the toric code with string tension, the 2D classical Ising model, and class D superconductors. So that's the stuff that I'm going to be talking about most. I should mention that this is work that I'm doing together with Alexander Jahn, who is contributing the numerical simulations to this project, Jens Eisert and Alexander Altland, who is unsurprisingly responsible for adding the randomness into our project. Okay, so what we will be concerned with in this talk is a one-dimensional space psi that is defined by a two-dimensional tensor network on various lattices. So we consider flat lattices with like a hexagonal tiling, or square lattices, which also correspond to flat curvature. And we also consider tensor networks on a tiling of the Poincare disk corresponding to a hyperbolic space. And basically, what we want to do is we want to describe properties of this one-dimensional boundary state in terms of a bulk theory for this two-dimensional tensor network. Okay, so the starting point of this project was a few years back when these blackboards are really heavy. When there was still a lot of debate on how tensor networks can be used to tell us something interesting about ADS-CFT. And so probably the most profound holographic principle in tensor networks or one of the most profound ones, was discovered by Harlow, Pascal, Postavsky, and Yoshida, leading to this nice acronym of petticoats, where essentially the motivation was to consider the Ryota-Kayanagi formula, which establishes a relation between the entanglement entropy in the CFT and the area of the minimal surface in gravity ADS bulk. And it's quite natural to consider this problem on a constant time slice of this ADS space. So this is the time direction in a tensor network language. So I'm not gonna try to tile all this space with a tensor network. But what you can, maybe I will. So these should all be regular, nice triangles. So if you want to calculate the entanglement entropy of a subregion on the boundary, then as a basic property of tensor networks, we know that the entanglement entropy should be upper bounded by finding the cuts through this tensor network, which produces the minimum entanglement between this bulk subregion and this bulk subregion. And if all these tensors are, so if this is translation invariant, this cut will correspond to a geodesic. Now, so from tensor networks, we will know that there's an upper bound for the entanglement entropy that corresponds to the Ryotaka-Yanagi formula. But the saturation of this upper bound is the actual non-trivial aspect. So what Harlow and co-workers discovered was that to saturate this upper bound, we actually want to have two ingredients. The first one is to have a hyperbolic lattice, so a tensor network that corresponds to a regular tiling of some hyperbolic space, like the Poincare disk. And the second property is that the tensors themselves are basically maximally entangling along all directions. Right, so I mean, the nice aspect here is that the Ryotaka-Yanagi formula really should only hold in a hyperbolic setting, and that is exactly what you find in this network picture. Right, so in the next step, like what Jens and Alex did some 5 years ago, was to consider instead of general tensor networks or perfect tensor networks, matchgate tensor networks, and to study the effect of the bulk curvature on properties of the boundary state. I will talk about, so I will come to the definition of matchgate tensor networks in a second, of matchgate tensors. And I think probably most of you are familiar with them, or if not, you've already seen them today. So they are equivalent to fermionic Gaussian tensors. So this makes them very suitable for numerical studies because they can be contracted efficiently. Okay, so in this matchgate tensor network picture, what Jens and Alex did back then was to calculate correlation functions at the boundary in hyperbolic and flat space. So this is the flat case, and the line here is a geodesic line from x to y. And the object of interest is the boundary correlation function of some operators on the boundary Ox and Oy. And what we found was the following. So if you plot the correlations as a function of the boundary distance, so the number of sites that are at the boundary separating x and y, not the geodesic distance, the boundary distance. For the flat case, you find exponentially decaying correlations. And in the hyperbolic case, you find a power law. Yeah.
Maybe we should write a formula so we remember.
But you see, there's a divergency for the 1 over r squared or something, and it doesn't decay as fast. So. Okay. But yeah, I agree. So I continue with the flat things here and the hyperbolic there. Okay, so we find that the correlation function exponentially.
So that's for matchgate tensors in the bulk?
Yes.
And it doesn't matter how you orient them, they're always matchgate tensors?
Orient them.
Well, I mean, matchgates is usually for circuits. There's a time and a space direction, and here it's like a big net on the inside of your...
So there's a regular tiling in the inside. So you should really look at the pictures above on the right that I drew before I actually started talking.
Right, but for that it doesn't matter how you... So matchgate is matchgate in all cuts? Never thought about that.
So matchgate, so if you contract two matchgate tensors, you get a matchgate tensor.
Okay.
So the distinction of the two diagrams is the effective curvature that you get from the tiling. So if you have like a 3-6 tiling or a 4-4 tiling, so where 4 denotes the number of plaquettes and okay, 3-6 is better. So 3 is the triangular shape, and 6 means you have 6 triangles around plaquette. So in this lattice on the right, you have a 3-7 tiling, so still triangles, but 7 triangles around one vertex. So this effectively corresponds to a negatively curved space. If you think of all these triangles being equally in size, and it's just a projection to the 2D plane, it makes it look so weird. But yeah, in both cases, you get a matchgate tensor network. So the whole contracted tensor network is just one big matchgate tensor with open indices as one.
Is there something that prevents you to go through elliptic geometry?
No.
That's not interesting.
Probably not. I'll tell you why during my talk. Okay, so right, but this is found if you consider the boundary distance. Now, if you actually consider the geodesic distance, this is proportional to the boundary distance in the flat case. But in the hyperbolic case, this is actually proportional to the logarithm of the boundary distance, because I mean, you see from the picture that the geodesic distance is much shorter than the distance at the boundary, and there's a kind of inflation rule. So when you move from the center towards the outside of the disk, you double the number of tensors. You don't really double, but like 1.5, or depending on the particular tiling. So if you evaluate these correlation functions not as a function of the boundary distance, but as a function of the geodesic distance, you actually find exponentially decaying correlation functions in both cases, which kind of makes sense because these matchgate tensor networks generically correspond to a gap system, and you have exponential decaying correlations in it.
Is D in the exponential?
In the gap, yes, of course. That was the point of the whole argument. Yeah, so you find exponential decaying correlations in both cases if you consider the geodesic distance and not the boundary distance. So that is the first part of taking away some of the holographic magic in this matchgate tensor networks. What has also been studied was the dependency on these correlation length, or the exponent in the power law as a function of some parameter A. So I will tell you in a second what this parameter is, but let's just assume for now that in a translation invariant setting, you can choose your matchgate tensor network such that they depend on only one single real parameter A. And if you now look at the correlation length, the function of this parameter, there's an interesting thing going on. So for a certain parameter, which is the same in flat and the hyperbolic case, there's a sort of a phase transition where the correlation length diverges. Okay, so that is sort of what has been done before I started working on these things. And
the same AC?
yeah. So this is for a 3-6 tiling, and this is for a 3-7 tiling. You will get a different parameter for 4-4 tiling or 4-5 tiling.
That's a numerical result.
That's a numerical result. So first question was, can we understand this analytically? And can we understand like what is the origin of this phase transition? And then the second question we wanted to tackle was to ask, is this all of this that we observed there, is this generic, or is this due to fine-tuning and using a translation invariant setting with only one parameter? And to this end, we decided to study ensembles of matchgate tensor networks where the tensors themselves are basically coming from some Gaussian distribution. Yes.
A again?
Yes.
What is it?
Yes. I come to that now. I didn't tell you yet. I just said it exists.
But you are comparing zeta to zeta, right? So
I'm comparing zeta to zeta because
but it's not 1 over zeta.
well, you could call it 1 over zeta. So if you yeah, so okay, so yeah, well, so okay, so at this critical point, the correlation functions look exactly the same, but the part outside of this critical point, the correlations do not decay exactly between them. But both decay exponentially if you look at them as a function of the geodesic distance.
So I haven't understood well what is a Matscape tensor network, and my question is, you have 3-legged tensors,
Yeah.
right? So the Matscapes, the context, I know them, they're unitary, so they have, let's say, 2 input legs, 2 output legs. So I'm not fully sure what is this tensor network.
Yeah, I will answer both questions now. So matchgate tensor that we are looking at is let's say, so there are different versions, but I will consider a tensor with 4 legs for now, because the case with 3 legs doesn't, not everything can be explained nicely on the 3-leg tensor. And so we think of this as a, well, no, we don't think of this. They are defined as a tensor with 1 dimension 2. That is Gaussian in the sense that the so-called second moments characterize the full tensor. What I mean by this is that instead of specifying all T, I, J, K, L in this case, it is sufficient to specify sort of the 0 moment and then the second moment, which are just the configurations with 2 occupied points. So if I give you a list, so there are a few more that I don't write out here, but if I give you just the T0, 0, 0 entry and all the entries with 2 1s and the rest filled up with 0, the whole tensor is specified. So how does it work? So we have parity constraint, so all T I, J, K, L, where I, J, K, L under Z2 multiplication is not the identity, they are set to 0. And then what I mean by Gaussian or the following property. So the higher moment, in this case the only non-trivial moment is the fourth moment, is given by basically doing a big contraction, and it's given in terms of the second moment. So another way to write this, well, okay, so first of all, these tensors, instead of having 2 to the n independent entries, they have n over 2 independent entries, so just the so-called second moments. And you can neatly define them in terms of a so-called generating matrix if you go to a fermionic version of those. So let me just write this out and then explain what I'm doing here. Now the important part. Okay, so if I regard this two-dimensional vector space as a fermionic vector space, or a great vector space, I can identify occupied and unoccupied indices, or 0 and 1, with a fermion being present or a fermion being absent. And I can rewrite, or I can neatly store all the tensor components that are non-trivial as prefactors of some Grassmann valued polynomial. So in this case, we would have the identification of the zeroth entry with 1, and then these guys would correspond to what I always refer to as the second moment. Where this guy then corresponds to this fourth moment given by Pfaffian. Is the structure clear for those who see matchgates for the first time? Okay, so this is the crucial point is that you have a dramatic reduction of independent tensor components, and that you can express them essentially as a Gaussian free fermion function. So
so they're equivalent to Gaussian free fermion tensors.
Yes.
Okay.
Yes. I think there's no contradiction to also interpreting them as a unitary gate from 2 indices to 2 indices. Okay, maybe we should check this. So I never used any unitarity anywhere. They actually shouldn't be unitary because they are like the two group multiplication tensor. So we should maybe discuss which matchgates you have in mind. But yeah, I mean, this is the definition of the matchgate tensors that comes from studying perfect matchings and this holographic algorithms by Wayland and co-authors. So I think no co-authors. I'm not familiar with matchgates in the sense of unitary gates, so let's discuss this later. Okay, so what I've written down here is completely sufficient to understand the critical point that emerges in our tensor network. All we really have to do is to realize that the tensor network we're looking at is essentially a single copy of a toric code with string tension, or equivalently in classical Ising model partition function. So let me introduce the following notation. So this is the tensor that does Z2 multiplication of all its legs and splits out 1 if they multiply to the identity, and otherwise it splits out 0. So this is what you can use to construct the ground state of a toric code. If you want to establish a correspondence to matchgate tensors, so and now I also tell you what this parameter A is. So in this previous work, they considered a special random matrix A, which was specified by just a single parameter. So you have the following matrix. So this parameter is all that enters the tensor network, and it's exactly this guy. Now, if you want to encode a matchgate tensor network in terms of these Z2 tensor network, or these Z2 tensors, all you need to do is to add weights. So essentially, what this tensor network represents is so assuming we would set A to 1, then each of these tensor components here would occur with the same weight. So also this guy here, because 1 minus 1 plus 1 is 1. So if we consider the tensor network, and say we specify some boundary conditions, say these two bonds at our boundary should be occupied, then the tensor network contraction evaluates to all allowed configurations, which is just the superposition of all closed loops. So we could have this guy, and if we had like a larger tensor network, we could have more complicated strings connecting our boundary sites and lots of small or long loops in addition to that, because all that this guy does is to implement a Z2 constraint. Now, if we move away from this A equals 1 limit, we have to incorporate weights, because now if we have A between 0 and 1, this effectively means that strings are suppressed because there's like a diminishing factor of A per segment. And for this guy, which corresponds to 2 segments, we have a factor of A squared. So it's really exactly a penalty for having a string. So we can equivalently express a matchgate tensor network of this structure in terms of a Z2 tensor network with additional weights that penalize strings. Now this essentially is a toric code with string tension. The only difference is that we don't have any physical indices here. So to see the correspondence to the actual toric code, we would need to consider 2 copies of the toric code and do the contraction of the physical indices. And then it's a matter of traveling around delta tensors and Z2 tensors to see that we get exactly the same thing, but with a squared.
So it's more a boundary theory of a toric code or
Yes.
entanglement vector of toric code.
Yeah. And now, I also said that we can understand this as a classical PI model. So this basically boils down to Hadamard transformation. So some of you who are more familiar with like I don't know, Hopf algebras or MPO symmetries or this kind of things, probably know that Z2 tensor under applying Hadamard transformations on each leg goes to a delta tensor. Now, if we apply a Hadamard transformation, so if we insert an identity here at each leg, we immediately obtain delta tensors at all the vertices, and the weights get conjugated by a Hadamard. So what this does is, I'm probably getting the signs wrong. But this is nothing but the transfer matrix of the classical 2D Ising model that Paul has discussed this morning. So basically this tells you the weight of the partition function for 2 spins that are next to each other and are both down. This is the element for both up, and these are the odd spin configuration entries. Okay, so basically we could stop here and just say, okay, the Ising model is known, we can calculate this by looking at the literature. What I found a bit nicer was to take this one step further and to map this guy to a free fermion Hamiltonian, where you can then calculate the critical point just by looking at the spectrum of this Hamiltonian. So the band gap closes at this critical point. And we were also interested in the question if, okay, so in this whole toric code business, I should say that this things over here corresponds to a topological phase. So we have at A equals 1 the equal weight superposition, the plane toric code. And if we move towards very small a, we have large string tension, so strings are penalized heavily. Basically, in the end, we will end up with a vacuum configuration. So when we map this, so this matchgate tensor network to a free fermion tensor network and look at the Hamiltonian interpretation of this guy, we were wondering if there's like a single particle topological transition going on at the same point. The answer is yes.
Is this similar to the Chalker-Collington network transition?
Yes. It's similar, it's not exactly the same.
How is it different?
I just, yeah, I have to admit, I just found it very recently that this exists. So I haven't compared it in detail, I should. But I suspect that because it's a nice mapping and it's an exact mapping, and there are only so many exact mappings in theoretical physics, we're probably reinventing the wheel. So I'm not claiming novelty. But I think at least the topological transition, like the single particle picture topology, that hasn't been studied. I think there's no Chern number calculation in the Schortner paper.
No, but that is single particle, right? Superconductor is a single particle transition.
Yeah, but they didn't study, they didn't view it under the lens of topological insulators and way.
I mean, technically not, but I guess like I thought it was understood that was a topological phase transition between, I guess in their language, plus or minus a half.
Okay. Yeah, as I said, I'm not claiming novelty. It's yeah. Unfortunately, I'm not familiar with everything that has been done in the last okay, so let me proceed to the free fermion business. Okay, so we have seen that a single tensor can be represented basically as an exponent, so a Gaussian Riemannian Gaussian function. And one more thing that we need to consider is how the contraction of two tensors is represented in this Riemann language. So it's basically just doing a projection to maximally entangled pair, which you can write formally as integrating out the two fermionic modes that are associated to these two vector spaces. You have to be a bit careful with the ordering of the fermions in the contraction. But at the end of the day, you can also represent the one contractions by a Gaussian Riemann function. And if you then stitch everything together, the whole state can be written as an integral over all the Riemann modes in bulk. And something that I would call maybe a pseudo-Hamiltonian for now, because in general this guy doesn't have to be, this is not Hermitian. But what this Hamiltonian looks like is just the collection of all the individual A matrices that define the individual tensors, and then the adjacency matrix of the tensor network that captures all the bond connections. Right, so let me erase the blackboard. Are there any questions up to this point?
Now you have defined the tensors with like 4 legs. But, in the motivations at the beginning, you were say, going with 3 legs, and was affected by matching them. You were getting curved surfaces.
Yeah, you can study. You can study all versions. The reason why I chose to discuss 4 legs here is that if you only have 3 legs, then you only have the second moment, so I cannot really say how the fourth moment or how the higher entries are defined in terms of the lower ones. So that's why I chose 4. But it's exactly the same construction. If you have a triangle, then you just forget about the last row and the last column. So what I'm doing now is I'm redrawing this tensor network just in another slightly modified version, but it's still the tensor network on the square lattice. Now I just want to make the connection to single particle physics more explicit. So if we just forget about, so we know how to arrive at this Hamiltonian from the tensor network by just collecting all the individual tensors and the adjacency matrix. And now I forget about the tensor network and everything, and I just treat this as a, or maybe I treat this, because this is emission, as a single particle Hamiltonian, which is next neighbor, because well, the A matrices, these entries here, they basically correspond to couplings between fermionic modes inside a unit cell, and these this adjacency matrix is just a coupling between modes in different sites with weight 1. The one which just comes from the tensor network, there's nothing we can do about it. But here we have like couplings A12, A23, and so on and so forth. Now, since this is a nearest neighbor, it's essentially a nearest neighbor hopping Hamiltonian, and in the translation invariant setting, so if we have the same tensor at each side, we can write this guy in momentum space. Where we just have like a momentum in x and y direction corresponding to the hoppings from one unit cell to another. And if we evaluate, so I mean, first we can reduce this, okay, we can look at the band structure of this guy, and we find a band gap closing at exactly this critical point. And we can, like if we look at this band structure, so we look at the spectrum over the Brion zone, we, at this critical point, we see a useful rock cone. Yeah, and what we also did was to calculate the churn number associated to the line vectors, and we found the churn number going from 0 to 1 at the point of the phase transition. So apart from the fact that this is probably all 21 years old, this is quite a nice finding. But so we didn't stop there. So what we wanted to consider as well was the question of how robust all of this is if we go away from the translation invariant setting, and if we consider an ensemble of random tensor networks instead of just a single fine-tuned point. basically what happens next is to consider this free fermion Hamiltonian in the presence of disorder, and what we can do then is to derive an effective description of our systems in terms of nonlinear matrix model. And yeah, because I think that maybe nonlinear matrix model and the derivation of the latter are something that some of you have seen maybe quite some time ago. I actually want to give you some of the details of the derivation, because I think it's quite instructive to view this in a kind of tensor network language. Okay, so the object of our interest is the correlation function, and for the sake of completeness, I specified here to look at density-density correlations, and because we consider states where there are some random components in our tensor network, we cannot assume anymore that our states are normalized, so we better normalize them. And we will consider this quantity in an ensemble average, where the ensemble is given by using the A matrices so choosing the entries of the A matrix from a random from a Gaussian distribution. So we have some non-zero first moment, and then second moments given by some distribution. And so what I'm going to do next is to derive an expression for this in terms of a nonlinear sigma model, and this proceeds in a few steps. So first of all,
So all tensors are the same.
huh?
The tensors are all the same. It's just that
No, they are.
every A is different.
Okay, so so make this clear. So okay, so we have so at each side x there's a tensor A, which has like elements aij, and they have a fixed mean that is the same for all of them, but then they like are scattered around this mean with a certain distribution. Okay, so what we know so far is how to express a single state in terms of integral over Riemann variables. Now, if we want to consider the norm of the state, what we need to do is to look at one layer that corresponds to the bra, one layer that corresponds to the cat, and then do the contractions along the open physical boundary. So in this Riemann language, that corresponds to now performing an integration over all Grossmanians, not only the bulk ones. And also, what we are doing is we introduce a second layer where the exact same bulk Hamiltonian lives, and we couple the two along the boundary. So this is just an identity matrix at the boundary, and the -1 here comes from taking the reversing the order of the bra versus the cat layer when we're dealing with fermions. Okay, so then if we want to calculate observables, this can be done by introducing source fields. So if we add our now double layered Hamiltonian, and I'm writing it like a set notation here. We further introduce some source matrix J, such that if we take the derivative with respect to some entry of this matrix, some combination of theta and theta bar becomes a sort of integral, which corresponds to, for example, the density. Now probably the most interesting part is to do the normalization. So we know that calculating this Riemannian integral is nothing but the Pfaffian of this large matrix over here. And since this is a norm, this is positive, we know that this is given by the square root of the determinant. And so if we want to divide by the norm, we can do this by introducing another Gaussian integral over fermionic variables. The only problem is that due to the antisymmetry of this Hamiltonian, this expression is actually identically 0, so we cannot use this. So what we do instead is to basically expand by another Pfaffian, such that we can introduce sort of a doubled matrix, which then is no longer antisymmetric and but has the same spectrum, so we can use bosonic variables to perform this normalization. So this guy has a purely imaginary spectrum. So we also need to add some convergence factor to this. And when I first derived this, I thought that was a pure technicality, and I didn't really understand the significance of this. But apparently, if you have like a single particle antisymmetric matrix, this corresponds to a superconductor in the Majorana basis. And it is known that like these superconductors without any further symmetries have like this inbuilt double space symmetry. So it's I think that the physical origin of this is the inbuilt particle hole symmetry. Unfortunately, I'm not an expert on this, but let me just say that this like doubling trick and the convergence factor is most likely not with the technicality, so it's most likely representing some physical mechanism that captures the right symmetry class of our system. Okay, so now with this setup, we are ready to finally express our correlation functions in terms of a free field partition function, which is composed of bosonic and fermionic variables. So we have essentially a supersymmetric free action. So this guy here contains fermionic and bosonic degrees of freedom. Okay, and what we are doing next is to add the disorder to this. And we can do this quite explicitly because we can parameterize the disorder part of our Hamiltonian explicitly by another Gaussian integral. So we have the non-disorder part and the disorder part of Hamiltonian, and then a Gaussian wave. As TR denotes the supertrace. Okay, and so to derive at the final form of this expression, which is this matrix model that I have mentioned quite a few times by now, we do the following transformation. So if I represent the scalar product of psi bar and psi in tensor network notation, and the disorder Hamiltonian by this matrix, then the scalar product here has the following structure. So there's a contraction involving the disordered Hamiltonian that essentially affects the space degrees of freedom. But there is a whole bunch of other degrees of freedom that is not affected by the disorder, because the tensor network with this double layer structure, this is the same state in the bra and the cat layer. So the disorder elements are identical in the two layers. So there's another Hilbert space that contains this double layer space, and then also the sort of artificially introduced double space that we needed to construct the bosonic integrals, which we, due to the analogy to the conventional superconductors, we call advanced retarded space, and also the space of fermionic and bosonic variables. So there's a second Hilbert space here that the disorder is not affecting. The goal of the two next derivations is essentially to shift to get rid of the disordered part, which lives in the spatial the Hilbert space associated to space degrees of freedom, and shift it to this other Hilbert space. This is done by a Hubbard-Stratonovich transformation, but I find it more elusive more enlightening to draw it in this tensor network notation. And this has the goal of doing this shift is that we then can use so first of all the effective theory that we arrive at will be slightly simpler than this, because we will have less microstructure to deal with, and also this advanced retarded space symmetry will turn out to be become relevant if, because this tiny convergence factor actually affects the structure of our stationary solution. But this is maybe too technical, so let me just proceed with finishing this derivation here. So okay, so we have a Gaussian integral to do. We do this by performing a completion of the square, and then just integrate out the disorder. So this happens in a pictorial notation in the following way. So we take our bra and cat layer, and take the trace of these two guys squared. So if we measure this, we get the trace of the disorder part, and we get the coupling of the size to the disorder Hamiltonian, but we also get a quartic term. So we need to subtract this quartic term. And now we will introduce a set identity. So this is this Hubbard-Stratonovich transformation. So we introduce another. Let me not call this a. Call it N. So we introduce another matrix, but this matrix now, instead of acting on the space degrees of freedom, acts in this other Hilbert space. So instead of considering this guy as a matrix in real space, we now consider this object as a matrix acting in the other Hilbert space. So if we introduce this Hubbard-Stratonovich field M, and shift it by exactly this expression, then we can remove the quartic term again, and what we are left with is the same structure as before, almost, with a crucial difference that we have gotten rid of the disorder Hamiltonian acting in space, and instead introduced the supermatrix valued Hubbard-Stratonovich field that acts in this double layer AR and super. Okay. Yeah, yeah. so if we also integrate out the fermionic dilution, sorry, like the size of superconductors, we arrive finally at this nonlinear matrix model. So this is the action of our effective theory. This is just a Gaussian weight, so it's not that important. But this trace log term here essentially contains all the information of the structure of our like theory. So this effective action is known in the theory of like disordered superconductors. So basically class D system, so a BDG Hamiltonian with no further symmetries. The nice thing is that it allows us to actually calculate our correlation functions analytically in the case of disorder, on average at least. But unfortunately this, oh sorry, I should have, these are all M's. Unfortunately the evaluation of this integral is a bit tricky. So basically the starting point here would be to consider the stationary points of this action, which we did. And what we find is that essentially this convergence factor determines the structure of the stationary solution. And now this is an instance of like usual spontaneous symmetry breaking, where the stationary solution has less symmetry than the action that we started out with. So we can evaluate the corresponding Goldstone manifold that is given by the symmetries of the action that we started out with, modeled out by the symmetries of the stationary solution. And unfortunately, this manifold is quite complicated. So it's we know the structure, but it's like 10-dimensional in the bosonic sector and 4-dimensional in the fermionic sector. So there's no way we can perform these integrals exactly. So the hope is that it is sufficient to expand this action around the stationary point with some like slowly varying fluctuations that aren't too drastic. And when we do this, skipping a few details, but this is just like technical stuff expanding this trace log, and then performing a continuum limit. So at the end of the day, what we find is the following effective action. And well, we were quite happy to rediscover the metric of the lattice that we started out with. So if we consider this lattice, we can go to a continuum description of this because we're assuming that we have slowly varying fluctuations. So the fluctuations are much larger than the lattice spacing. So the fluctuations happen on a scale much larger than the lattice spacing. And essentially, because this is the nearest labor Hamiltonian, we end up with the dominant contribution of our effective action as a Laplacian. So this is the Laplace-Beltrami operator corresponding to the metric that is given by the tensor network lattice. And we can calculate the correlation functions, so that by taking the derivatives with respect to the sources that I didn't write here, but at the end of the day, all we have to do is find the resolvent of this this operator, where the main part is a Laplacian, and this is like a massive term at the boundary. And now so now the surprising thing that is actually happening is that if you look at the Laplace-Beltrami operator for a hyperbolic disk, and you look at the corresponding metric, then there's an exact cancellation of the prefactor from this Laplace-Beltrami operator and the metric. So our prediction from the field theory is that the correlation function looks exactly the same, regardless of whether this is flat or hyperbolic, which is like another loss for the holography story. But it's actually consistent with the numerical results that we performed. And sort of the solution to this puzzle is, or let's say, so why is it consistent? Because I just told you earlier that we get exponential or power law decay as a function of the boundary distance. So this is again as a function of the boundary distance. The solution is basically following. So our theory is only valid at the critical point. So for our theory to be valid, we need a finite density of states at 0 in the single particle picture, which means we need basically a gapless clean system to start with. So to summarize the whole thing, what we have done is to derive an effective field theory that describes matchgate tensor networks at the critical point with a certain disorder. So there's basically the disorder strength enters here, and it determines the decay rate of the correlation function. But yeah, so to cut it short, we have developed an effective field theory description of the critical point in these matchgate tensor networks, which reveals no dependency on the geometry of the lattice, which maybe is also not very surprising, because it's like in another language it's a topological transition, so it really shouldn't depend on details like the geometry. But yeah, so what we would really like to do next is to consider beyond matchgate, so consider weakly interacting tensors. So if we just add quartic terms, we can still use the same machinery because we're dealing with quartic terms anyways, but we would just be able to describe way more general tensors than matchgate tensor networks. For example, if you have a triangular tensor, if you add a quartic term, you're almost fully describing the parameter space of the full interacting tensor. Yeah, so this could be potentially a way forward to having a single particle effective field theory description of general fermionic tensor network to some extent. Yeah, that's it.